Good morning, students. Today I plan to do lateral displacement from ray optics chapter. So let's see what is lateral displacement. So let me take a glass slab. Okay, I take a glass slab like this. This is a glass slab, and then so this is the glass slab. Okay, so a ray is incident on this glass slab. So we call this glass slab as ABCD, and then we allow a ray incident on this face, and then because it is a glass slab, the ray will be refracted, and then this is my normal, and then I extend this normal to till this point, and this is my L dash, this is L. Okay, so after this refraction, this ray will move towards the normal, and from here it moves away from the normal. After refraction from this face, it will move away. Okay, this is the normal here. This is the normal, and so this is the incident ray. It is after refraction, it is going like this. So it moves from this rarer medium to denser medium. The ray move towards the normal, and then if it moves from denser to rarer medium, again it moves away from the normal. And this is the first angle of incidence. Let's take it as I1, and this is R1, angle of refraction at this face, and here this is I2, and this is R2. But if we don't have this glass slab, what will happen? If there is no glass slab, this ray will go like this without any refraction. But because of this glass slab only, okay, because of this glass slab, the ray is moving, is got refracted. Otherwise, it will move like this only. So, which means the ray is displaced from here to here. We call that as the lateral displacement. So, I draw a perpendicular from here. Take this as M. This is N dash. This displacement of rays because of this refraction is called as this lateral displacement. So I want to find expression only for this M N dash. This is my lateral displacement. Okay, and then the ray which supposed to go along this way is now going along this way. Therefore, this angle is called as angle of deviation. Okay, you can see this I1, this side it is R1 plus delta. So opposite angles are equal. Therefore, this I1 will be delta plus R1, and this I1 is equal to delta plus R1, and delta is equal to I1 minus R1. This will be used later. So I keep this equation as it is. So I'm going to apply Snell's law first in this face AB. So applying Snell's law, first in face AB. Snell's law formula is refractive index of the second medium, because here the second medium is glass, first medium is air. Refractive index of the second medium to the refractive index of first medium is equal to sin I1 by sin R1. So we call this as mu refractive index of glass with respect to R. Similarly, in phase CD, if I apply Snell's law, the ray is moving from glass to air. Second medium is air here. This is air. This is glass. Ray is moving from glass to air. Second medium is air. So refractive index of air with respect to second medium with respect to first medium is equal to sine I2 by sine R2. So this side it is refractive index of air with respect to glass. So if I keep a mirror, what will happen? Here if I keep a mirror, okay, and then this I label this point as N. I keep a mirror, what will happen? The ray will retrace its path according to the principle of reversibility. Okay, so by principle of reversibility, this mu AG or mu GA is 1 by root 1 by mu AG. This is principle of reversibility. So I substitute the formulas from here. So I will get, I substitute the formulas in this equation. Mu AG is the first one. This is, so this side it is sine of I1 by sine R1. This side is 1 divided by mu GA, that is this equation. Sine I2 divided by sine R2. So it will go up. It becomes sine R2 by sine I2. And then this I2, okay, is equal to this R1 from this diagram because opposite angles. So but I2 is equal to R1, so substituting here, so you will get sine I1 by sine R1 is equal to sine R2 divided by, instead of I2 I substitute R1, so I will get sine R1. This sine R1, this sine R1 will be cancelled. So you will get sine I1 is equal to sine R2, therefore I1 is equal to R2. Because sine I1 is equal to sine R2, therefore I1 is equal to R2. What is the meaning of it? I1 is this angle, R2 is this angle, which means this ray is parallel to this ray. That is, this ray we call it as KL. Okay, so this, therefore I got one important result. This KL is parallel to this final ray, that is MN. This is MN. So it is parallel to MN. Okay, so I want only lateral displacement. Let us now find the expression for lateral displacement. I want lateral displacement this Mn dash, correct? This is what I want. Okay, so I want to find this lateral displacement Mn dash. So this angle delta is MLN dash. So angle MLN dash is equal to delta. So sine delta is nothing but, so MLN dash, sine delta is nothing but opposite by hypotenuse. This opposite side is Mn dash, hypotenuse side is Ln. So I want to find only Mn dash as I told. So I'm just rewriting this formula. Mn dash is equal to Lm sine delta. Okay, now I want to find sine delta and then I have to substitute here. So what is LM first? Let take this triangle L dash M. You take from triangle L dash M. So what is that L dash M? Where is that? This is the triangle I'm looking for, L dash M. I'm finding cos R from here. Cos R1 is adjacent side. This is L dash. Okay, adjacent side is L dash divided by hypotenuse side is the longest side, that is LM. L this is LM. So L dash is equal to T by LM. From here you can find LM. LM is equal to T divided by cos R1. So this LM I can substitute here to find this MN dash. So now it is simple. You have to find only MN dash. This is the lateral displacement. You substitute for LM. You will get T by cos R1 sine delta. Now Mn dash is equal to T by cos R1. This is cos R1. And instead of this delta, I already told the value of delta is I1 minus R1. So it will become I1 minus R1. Okay. So I am writing this expression here. Mn dash is equal to T by cos R1 sine of, okay, I1 minus R1. This is the expression for lateral displacement. I hope you understand this answer, but this answer is very important. You write one time and then you see. So try to do it again and again so that it will become easy for you. See you in the next class. Thank you so much for watching.